Okay, if you've been working in AI at all, you've heard about vector embeddings. They're basically the secret sauce, right? They turn all our stuff, words, pictures, sounds, into numbers that AI models can actually work with. But there's this huge question that always comes up. Are they standardized? Well, that's the paradox we're going to get into today. So let's frame it like this. You know how a JPEG just works? You can open it on any computer in pretty much any app. Same with an MP3. Plays on your phone, your laptop, wherever. So the big question is, can you do that with embeddings? Could you take an embedding made by OpenAI and just slot it into a system that was built for Google's embeddings? And here we go, the classic, well, yes and no answer. The short, direct answer is a big no. You can't just swap them out. But, and this is a huge but, that's not the whole story. While the embeddings themselves are kind of locked into their own little worlds, the way we use them, that playbook is surprisingly standard across the board, and that's the core paradox we're going to unpack. All right, so let's tackle the no part first. Before we can get to the nice, orderly, standardized process, we gotta understand the chaos. Why aren't these things just universal? Why can't they all just get along? And here it is. This is the root cause of the whole issue. An embedding isn't just a list of numbers. It's a very specific, learned representation of meaning. It's defined by one, and only one, AI model, with its own unique training data, its own architecture. You could almost think of it as a little snapshot of that model's brain. So since every model has its own unique brain, trying to mix and match their outputs, well, it's kind of like trying to mix oil and water. It just doesn't work. Let's dig into exactly why that is. This is honestly the best way to think about it. The numbers from an OpenAI model represent concepts in, let's say, the language of French. Now, if you take those numbers and give them to a system that only understands Japanese, the language of a Google model, the meaning is just gone. It's totally lost in translation. And if that language analogy wasn't enough for you, here's the cold, hard proof. It's a physical thing, too. Just look at the dimensions. That's just how long the list of numbers is. OpenAI's model here, it's got 1,536 numbers. Google's is 768. A common open source one might have just 384. They are literally different sizes. Which brings us right back to our puzzle analogy. It's not just that they're speaking different languages, they're fundamentally different shapes. You just can't do a direct comparison. It's impossible. Okay, so the embeddings themselves are a bit of a mess, right? Not interchangeable at all. But here's the twist. This is where order comes from all that chaos. Because while the what isn't standard, the how we use them absolutely is. The entire industry has kind of settled on a very reliable, standardized playbook. Think of it like a car factory's assembly line. You might be building a tiny sports car one day and a giant truck the next. The final products are totally different, but the steps on the assembly line, they're pretty much the same. Build the frame, add the engine, paint the body. It's the exact same idea with embeddings. And here is that assembly line. This is the standard workflow you see everywhere, especially for things like retrieval augmented generation, or RAG. It's a simple 4-step dance. Step 1, you grab your raw data. Step 2, you pick one single model and stick with it to turn all that data into embeddings. Step 3, you store all those shiny new vectors in a special vector database. And step 4, you use standard math to search through them. That's it. This process is the de facto standard. Right, so that brings us to that crucial last step. If all of our embeddings were made by the same model, they're all speaking French, how do we find the ones that are most similar to our search query? Well, the answer lies in the one universal language we all have, math. The most popular kid on the block by far is something called cosine similarity. Now, if you want to get technical, it's calculating the cosine of the angle between two vectors. But what on earth does that mean? Simply put, it's just checking to see if two vectors are pointing in roughly the same direction. So let's put that in plain English. Cosine similarity doesn't really care how far apart two things are in space. It cares about their direction. It's a way of asking, hey, are these two different ideas, these two chunks of text, basically talking about the same thing? Are they pointed at the same meaning? And for finding related concepts, that is incredibly powerful. And hey, cosine similarity isn't the only tool in our toolbox. It's the star of the show for text, for sure. But we've got other standard metrics too. You've got Euclidean distance, that's just the straight line distance between 2 points, and dot product. The big takeaway here is that there's a small, well-understood, and agreed-upon set of math tools we use for these comparisons. So, we've got non-standard embeddings. but we've got a standard process to handle them. All of this leads to one single, absolutely critical, non-negotiable rule that you have to follow if you want any of this stuff to actually work. And this right here is the main takeaway of this whole explainer. Every single part of your system, the part that creates the embeddings for your database and the part that creates an embedding for your search query, they must use the exact same model. No exceptions. It's the only way to make sure everyone's speaking the same language. So, if you remember just one thing from all of this, let it be this simple phrase: same model, same rules. Always. That is the golden rule of working with vector embeddings. Which leaves us with a really fascinating question to think about. Right now, all these models live in their own little universes. But, people are working on this. Researchers are trying to figure out how to translate between these different embedding languages. So the question is, will we ever get a Babelfish for AI? A universal translator that lets any embedding be understood by any system? Well, I guess only time will tell. Thanks for tuning in.